There's an invisible force shaping our lives, affecting the weather, climate, land, economy, and whether a flag looks majestic or just kind of sits there. I'm talking, of course, about the wind. Large parts of the globe are brought warmth and water thanks to wind. In Europe, wind energy is one of the most popular renewable energies, thanks to wind turbines that harness its power. Ships with sails have followed the path of the wind for centuries, bringing trade and entire empires along with them. Fierce winds can also bring destruction, stripping soil away from the ground or even ripping apart buildings. Trying to protect ourselves from the wind might feel like we're battling an imaginary foe, but wind is definitely not imaginary. Geographers have defined it and have tools to measure it. Whether it's a gentle sea breeze or gale force gusts, wind is any horizontal movement of air. And air is a mixture of nitrogen, oxygen, and other gases that blend together so well they tend to act as one. Winds are named based on what direction they come from, and some people are even named after winds. My name, Alizé, means the northeasterly trade winds in French, or les vents alizés, the Alizé winds. With a French sailor for a father who used to love sailing the warm northeasterly trade winds, it's no surprise where this came from. So let's get deeper into the science of where wind comes from. It'll be a whirlwind of an adventure. I'm Alizé Carrère, and this is Crash Course Geography. If we zoom out and look at the globe as a whole, we can see that there are global wind patterns just like there are global air temperature patterns, and these are intimately linked. We know that insolation from the sun doesn't get distributed evenly and ends up heating places differently. The temperature of a place is tied to several key factors like latitude, elevation, how far it is from the ocean or sea, and even what type of surface it is and how much of the sun's energy it absorbs. No matter where we are though, air that's warm is lighter, less dense, and tends to rise. Cool air, on the other hand, is heavier, more dense, and tends to sink. And you did hear me correctly. There's lighter air and heavier air because air molecules all have weight. Not a lot, but still weight. The weight of air then leads to atmospheric pressure, which comes from all of the air above that's pressing down on whatever air there is below. So the pressure is much higher where I'm standing in Miami than if we were filming this close to outer space. Down here, there's all 480 kilometers of atmosphere squishing down on us. In fact, it's likely close to standard sea level pressure, which is exactly what it sounds like. The average atmospheric pressure at sea level. We don't crumple like aluminum cans under this enormous pressure because the air and water inside us exert an equal amount of pressure outwards. And the exact atmospheric pressure in other places will be different depending on where we are, the season, or even the time of day. Wind is actually the atmosphere's way of smoothing out pressure differences, which can be created by the daily and seasonal air temperature patterns across Earth's surface. Meteorologists who study the atmosphere use air pressure measurements to forecast the weather. Like a weather report on TV might show a map full of H's and L's, which is actually a map tracking air pressure. A giant L stands for low pressure, or a low. On a global scale, a low area is where the pressure near the surface is less than standard sea level pressure. But on a local scale, like on your local weather report, a low can also be an area where the pressure is less than in the surrounding area because there's actually slightly less air pressing down on that part of the Earth. Lows go by lots of names, like you might hear it called a depression or even a cyclone, though it's not the giant spinning vortex of air we might think of. That's a specific weather event that only forms in tropical oceans. But we'll come back to that in upcoming episodes. To keep it simple, we'll just call it a low. Lows exist either because air is being heated and expands up and out, or air higher up in the atmosphere is spreading out, so there's less air pressing down on Earth's surface. Down on the ground, we might even be able to tell we're in a low. As air expands and rises, winds are drawn toward the center. The rising air cools and moisture in the air condenses into droplets. So if we happen to be in the center of a low, the weather would often be pretty cloudy and rainy. The giant H's on the map mark high pressure areas, which we call a high or anticyclone. In a high pressure cell, either the air is cooling and becoming denser, so it sinks, or the atmosphere high above is piling up, pushing the air below it downward. Sinking compresses air molecules together and makes them warm, so any water vapor in the air won't cool to condense into liquid water. That means high pressure systems bring weather that's clear and sunny, which I remember as H stands for happy. High and low pressure cells are usually large, like they can be 1,000 kilometers across. And air moving between these vast areas to balance out energy in the atmosphere helps us understand and identify the winds. The key is the difference or change in pressure between highs and lows, which is called a pressure gradient. Like any fluid, air wants to flow from high to low pressure. Let's start on a small scale and look at an island. When the beaches and land warm up faster during the day than the surrounding sea, the air over the island expands, rises, and lowers the pressure at the surface. That leaves room for air from the sea to rush onto the land, and voila! Any windsurfer or suntanner will get a cool sea breeze in the afternoon. And similar things happen at a bigger scale across the globe. Air at the equator is consistently warmed by the sun and tends to expand and rise, so we get a belt of low pressure around the Earth called the equatorial trough. And we'd expect the poles to experience high pressure because the air there is cold and sinking. But winds don't just blow north and south. This is because the Earth rotates. To see what really happens to these winds, let's imagine we're flying an airplane from the North Pole to the South Pole, with a layover in Ecuador on the equator. Let's go to the thought bubble. Hello, this is Captain Carrere speaking. If you look out the windows, you'll see the surface of the Earth slowly rotating eastwards. So in order to stay on a straight path, we'd have to constantly make little turns. This phenomenon that causes moving objects, like our plane, or air or water, to seem like they curve as they travel over the rotating Earth is known as the Coriolis effect. The Earth is rotating beneath our plane, but also as we travel towards the equator, the Earth actually rotates faster because the Earth is bigger at the equator and it has to move faster to keep up. It's like a marching band turning a corner. If they want to stay together in a straight line, the marchers on the inside of the circle take much smaller steps and move slower than the marchers on the outside. So if we're at the poles, we just kind of spin in place. But as latitude decreases, our rotational speed increases until we get to the equator and the Earth's surface practically zooms by at 1,600 kilometers per hour, which is about twice as fast as our plane. Then as our plane gets closer and closer to Ecuador and the equator, our rotational momentum comes from the slow speeds at the North Pole, not the rapidly rotating equator, which means we end up getting deflected to the right into the Pacific Ocean and have to make little left turns to get to Ecuador. Something similar happens on our second flight toward the South Pole, but this time we started out rotating faster than our final destination. So as we make our final approach to the South Sandwich Islands, we'd get deflected left and end up east of where we want to be if we didn't correct. Please make sure your seatbelts are fastened and your tray tables are stowed as we prepare for landing. Thanks, Thought Bubble. In general, the Coriolis effect deflects objects to the right in the northern hemisphere and to the left in the southern hemisphere, which is how we get those wind spirals around the low and high pressure areas on our weather map, and why they're also called cyclones and anticyclones. The air wants to rush directly from the center of the high to the center of the low, but gets deflected. So in our model, the heated air at the equator first rises upward towards the TROPOPAUSE, which is the boundary between the troposphere and the stratosphere, as it tries to move poleward high up in the atmosphere. Then, as it moves away from the equator, the Coriolis effect causes air traveling northwards to turn right, speeding faster east the further north it gets. The air is also cooling, and by the time it sinks back to the surface, it's only reached around 30 degrees latitude. So instead of one big circulation cycle, as proposed by George Hadley, an English lawyer and amateur meteorologist who first described it in 1735, we get a more complicated circulation system containing the Hadley cell. Hadley wanted to understand why surface winds that should have blown straight south towards the equator, along the pressure gradient from high pressure to low pressure, took a turn west. Solving that mystery would help ensure European trading ships would safely reach the shores and goods of the Americas. This isn't the first time our understanding of the winds has gone hand in hand with exploration, and trade, wealth, and power were driven by the winds. For instance, new technologies created in the 1400s, like the quadrant and the astrolabe, enabled accurate navigation and mapping of ocean currents, winds, and trade routes. Over the years, many more scientific minds have explored the implications of Hadley's theory, and we're still learning more as we explore the movement of energy between the atmosphere and the biosphere. We now know that in reality, air in both hemispheres converges in the narrow band around the equator called the intertropical convergence zone, and rises. The surface winds, or doldrums, that form here as air converges and rises upwards are light and not super reliable. Sailing ships could get stuck in the doldrums for days. Similarly, weak winds are found on the poleward edges of the Hadley cells, where air is being forced down, creating high pressure zones centered at about 30 degrees latitude called the subtropical high pressure belts. Sailors of yore were often forced to eat their horses or throw them overboard in these, quote, horse latitudes to conserve drinking water and lighten the weight while the sailing ships waited for the weak winds at the center of these highs to pick up. Wow, that's pretty dark. In between these high and low pressure belts, there are strong and reliable winds spiraling outward from the subtropical high pressure belt towards the equator. These are the easterly trade winds. And they're my favorite winds, obviously. Many ships have depended on the trade winds, like early Spanish sailing ships as they sought God, glory, and gold in what we now call Central and South America. Of course, making the return trip was another matter. The ancient mariners of the Spanish galleons going home from the Americas plotted a course using the winds blowing poleward from the subtropical high pressure belt. These westerlies are strongly deflected to the right and blow from the southwest. These strong winds blow towards another low pressure belt called the subpolar lows, where they clash with the polar easterlies blowing from the frigid, very high pressure poles. In the southern hemisphere, they blow with greater strength as there's very little land in these latitudes to interrupt their flow. So altogether, on our idealized Earth, we've seen that there are actually 7 pressure belts: 2 polar highs, 2 subpolar lows, 2 subtropical highs, and 1 equatorial low. And winds flow between these belts of high and low pressure. On the real Earth, the belts are not so organized. They form cells of pressure, and we see more complex patterns of pressure and wind as the cells shift with the seasons and vary between land and water. So our idealized Earth is kind of like a wind and pressure map. It's a simplified model that helps us understand what's happening on the real Earth. Just like the atmosphere works like a cell membrane, the winds are like Earth's circulatory system. So many things vital to our planet flow through the winds. During the voyages of discovery in the 15th to 18th centuries, which we now recognize weren't really discoveries at all, the knowledge of winds, ocean currents, natural harbors, and more was an essential foundation for circumnavigating the globe. And we continue to rely on the winds to power our economies. As a renewable energy source, this silent force will continue to shape our lives in the future. I hope wherever you are is in the center of a sunny, high-pressure area, which will be perfect weather to go with the flow in the ocean, which is what we'll talk about next week. Many maps and borders represent modern geopolitical divisions that have often been decided without the consultation, permission, or recognition of the land's original inhabitants. Many geographical place names also don't reflect the indigenous or aboriginal people's languages, so we at CrashCourse want to acknowledge these people's traditional and ongoing relationship with that land and all the physical and human geographical elements of it. We encourage you to learn about the history of the place you call home through resources like nativeland.ca and by engaging with your local indigenous and aboriginal nations through the websites and resources they provide. Thanks for watching this episode of Crash Course Geography. If you want to help keep all Crash Course free for everyone forever, you can join our community on Patreon.